This question involves a person at the origin here hitting a cricket ball along this path out this way, and the velocity of the cricket ball is given by 7i plus 24j. And then we've also got a fielder located at point A at 2i plus 3j relative to the origin here. So basically what's happening is we've got a fielder here, cricket ball being hit along in this direction here. Now, as part of the question, what we're required to find is the minimum distance that the cricket ball comes from the player at A. So as it moves along this path, what's the closest distance the ball is to player A? And that closest distance will actually be when the path is at right angles to the vector between P and A. So we can define this vector PA here as negative OP plus OA. And we can express that vector as vector OA 2i plus 3j, take away t times 7i plus 24j. And we've got the t there because 724 is the velocity vector. So to get the displacement vector, we multiply it by the time in seconds. Looking at the I and j components there, we can say that vector PA is 2i take 7ti and 3 take 24tj. So if we want to find this least distance, we know as it moves along this path here, at any point along this path, we could work out the distance from the path to point A. And clearly when it gets to this point where it's at right angles, that'll be the least distance. So we can use dot product to find that least distance. And if we just find the dot product of vector PA with the velocity vector 7i plus 24j, and set that equal to 0, that'll give us the time at which the ball is closest to player A. Okay, so you can see I've done this down here in part B of the question. So vector PA perpendicular to the velocity vector, 7i plus 24j. And we can actually do that calculation, the dot product, set it equal to 0 on our class pad, and we can even solve for the t value on our class pad. So I'll do that over here. So we just go to action, vector, and dot product. And then we go to math 2 and put in our vectors in vertical form there. We've got 2 take 7t. I'll use x instead of t just for ease of input. So 2 take 7x and 3 take 24x. And we're going to find the dot product of that with the velocity vector, 724. So again, enter another vector there in vertical form, and that one was 724. Close brackets. Now that expression for dot product will give us the dot product with respect to x or t in our case. Now we can even solve this if we like for when it's equal to 0. So I'll just go back to math 1 and input solve there. And I want to solve for when the dot product is equal to 0. And we're solving for x in this case. So what will this will do? It'll just solve for when this dot product is actually equal to 0, which will be the point of least distance. We'll press execute there. And there's our answer there, 0.1376 seconds as our answer. Now, of course, we wanted the distance and not the time. So to find the distance, all we need to do is, at that value of t, in our diagram here, for that value of t, we want to find this distance here. So effectively what we want to do is we want to find the magnitude of this vector when that t value is 0.1376 seconds. So again, really easily done on the class pad. So what I can do here on the class pad, now to find the magnitude of that vector, again we can get action vector, so norm finds the magnitude of the vector, and we want to find the normal of that expression there, but of course we want it when x is equal to 0.1376. So we could either substitute the 0.1376 directly in there from where the x is, or alternatively we could use go to math 3 and use the with symbol and just put that x equals 0.1376 in there, and that should find our distance. There it is, 1.08 meters, which is our least distance. Okay, so that's an example of using dot product to find the least distance between a moving object and a non-moving object, I guess. Now, alternatively, we could, for a question like this, instead of using dot product, we could just use the graphing facility of our ClassPad. So what that would mean is we could just, we've got this expression for the vector PA already, so we've got this one here, and we could graph the distance or the magnitude of that vector. So in other words, we could take the norm of that particular vector, 2 take 7t, 3 take 24t, and come up with an expression for that using our ClassPad. So I'm going to do that. I'll just copy this part here without the width and get an expression in terms of t. So there it is there. So it's a bit of a nasty expression, 625x squared. Just copy that down. So we've got 625x squared take 172x plus 13 it's to the power of 0.5, or the square root of that value. Okay, so that gives us the distance, and that distance is actually for any point along this path for a given t value. So what I should do there is okay, so we've got that expression there. In fact, that should be a t there rather than an x, just so we're consistent with our variables. So then what we could do is we could graph this distance on our ClassPad very easily. 625t squared take 172t plus 13 and find the minimum value. So on our ClassPad, I've already got the expression there, 625x squared take 172x plus 13 to the power of 0.5, or the square root. And I could just drop that into my, I'll just clear what's in there at the moment. So edit, clear. I could just drop this expression in there, it'll graph that expression, and then from there we can find the minimum value. So you can see there it is graphed there. It's a little bit hard to see, so what I might do is just change the viewing window so it goes from -1 to +1, or perhaps even from, yeah, I'll go from -1 to +1. So x min -1, max 1, press OK. So that's a bit of a better looking graph, and you can see our minimum value of distance will be at this point here, and that's pretty easy to find. Analysis gsolve min, and that hopefully should find it. There it is. So at a time of 0.1376 seconds, we get a least distance of 1.08 meters. So very easily done on the ClassPad.